I just hit record. So as you all know, I'm recording so that we can put them onto the little library that we have started on our website. So my name is Kelly Huff. If you have not been to one of these yet, I am the marketing manager for all 6 of our offices. So you might be from Texas, New Mexico, Arizona, or California. So welcome and good morning or good afternoon, wherever you may be. As usual, go ahead if you have any questions throughout, put them in the chat, and then we will go through them at the end. Let's see what else. That's really all I have for my announcements today. I'm getting shorter and shorter as we go. So as usual, we have Professor Dan Hani. He's our resident educator here at our Arizona office. And today he will be talking about thermally stratified environments. So Dan, go ahead and take it away.
Kelly, thank you very much, and thank all of you for joining us today. Really appreciate your time commitment, and glad you could join us today. Today's presentation is a little dense with material. So if I appear to be rushing, tell me to slow down. We've got a lot of material to cover for very good reason, because it really involves what solution might be out there to provide a healthier built environment, especially as we move into the era of post-pandemic. My name is Dan Hani. I am a senior, well, wait a second, do we capture the screen?
You're good.
We're good, okay, I'm sorry. My name is Dan Hani, sales engineer with Veritech Solutions. Many of you have been attending these webinars right the way through, and we greatly appreciate it, and are glad to know that obviously you find this time relevant. However, we do have a new group of people here, so just a quick introduction. I've been in the industry for 36 years. I started in 1985, actually 37 years now. My education was a little unique. I did do 2 years of chemical engineering at the University of Arizona before embarking on an art education, where I flew to England and went to Slade School of Art at University College London, where I earned my Bachelor of Fine Arts degree and my master's degree in sculpture at Boston University. I began my career in 1985 in estimating at Norman S. Wright, moving into sales. And then I joined Air Specialty Products as their first outside salesman in 2000, where I got into engineering sales. And in 2016, Veritech Solutions reached out to me because they saw what I was trying to do and advance HVAC designs to a high performance building concept. They reached out to me to see if I would join their team looking to the future of HVAC. And I did that as Veritech's lead educator for the corporation. So it's a little bit about my background. For any of you who may not know who Veritech is, we are a manufacturer's rep firm, but we've grown into the role of being an HVAC system solution provider. We have a presence throughout the Southwestern United States, from San Diego to Lubbock, Texas, and we can be involved and engaged in any system design concept for any type of building in the industry today, and welcome every opportunity to participate in evaluating what might be the best HVAC solution per the actual application or building usage. We can actually get involved in system solutions for variable refrigerant systems, mixed air VAV, packaged central plants, cloud-based controls now, underfloor air systems, 100% outside air systems, and all that is available in this compelling system design feature, as we hope to illustrate not only during today's presentation, but in future presentations. So our goal is really shaping the future of HVAC. And our mission statement is to provide here at the Veritech Technical Institute, to provide an educational platform for continued learning in the HVAC industry, with a focus on high performance building and innovative technologies for a better and healthier built environment, I might add. We have built this year a 13-part educational webinar series. We believe it's a little unique. Instead of doing showcase features each month, I decided to spend the first half of the session building a foundation of understanding of the principles of some of the technologies we're going to bring to bear to creating a healthier environment. And then after this presentation today, we're going to start looking at how we can actually integrate these various HVAC modality solutions into creating the healthiest indoor environments available in the market today, as we begin to explore in greater depth starting in September, right the way through January 2022. Before I begin today, I want to thank all of the resources I've drawn from as I did a deep dive. A lot of material to sift through, a lot of people to be thankful for. I personally want to reach out to Dan Inhout, who was a profound inspiration here at Veritech. Dan is a distinguished fellow at ASHRAE and leading educator in our industry on air distribution performance and beyond. Obviously, I rely on ASHRAE Fundamentals Handbook, ASHRAE Journal, and various independent test facilities and reports to do this. So today's discussion is we're going to evaluate thermally stratified environments. ASHRAE recognizes there are 3 HVAC strategies, and we're going to cover them. We're going to try to understand the physics of airflow in conventional mixed air systems and the nature of convection in thermally stratified environments. So our goal today is why displacement should be given to every consideration for post-pandemic HVAC designs. We will cover quickly a webinar series review. We're going to look at an update of CDC and ASHRAE and what they're saying on COVID-19. And then we're going to delve into the physics of room airflow. Well, how does air perform in a space at varying temperatures? We're going to then look at displacement ventilation, both in cooling and in heating, how air is distributed to the space using DV designs. And we're going to have a glimpse at innovative solutions such as 100% outside air systems. I think we're going to be looking at 100% outside air systems more frequently in the future for always making sure that we're bringing clean, fresh outdoor air into a building that does not have any risk of having pathogen entrainment. So a quick webinar series review. And if you're new to this review, please be aware all of these sessions are available on Veritech's website, and I'll show you how to access that material. Session 1, we covered ASHRAE's Epidemic Task Force and how to navigate their webpage through the various documents they have. And it is a substantial resource. I invite any of the design and owner community to go to evaluate what makes sense for optimizing the indoor air quality of your building. Then we looked at the physics of pathogen migration. How do pathogens from an infected index person travel throughout the space, and what are the influences on how that migration occurs? In session 3, we had Hoy Bohannon, distinguished lecturer for ASHRAE, present on ASHRAE Standard 62.1 and the importance of ventilation in creating healthier environments. Session 4, we did humidification. Why is having a properly humidified space an important consideration in reducing the risk of infection? In session 5, we explored the UVC technology, ultraviolet irradiation within the building, and learned ASHRAE's full endorsement of the technology and investment in expanding its research and how to apply it to the built environment. And then in session 6, we looked at needlepoint bipolar ionization, creating ion plasma fields in the built environment to not only reduce the risk of reduce concentrations of VOCs, allow for conglomeration of particles for better filtration, but also pathogen mitigation. So if you want to access any of these presentations, we invite you to go to Veritech's webpage at veritechsolutions.com. And then if you go to the training tab, click on the training tab, you'll come to a post of past webinars, and you want to click on the courses tab, and that'll bring you to this window here. It gives you each regional office and their local presentations, but if you click here at past webinars, you'll have a full access to all the sessions that we've given up till date. And if you would like a more focused session, reach out to Kelly, and I think we can obviously set up our own independent lunch and learn if you're a building owner or a GC or an engineer or even an architectural firm. I'm glad to work with you in providing those devoted sessions on any of the topics that we've already given. So what is the update for the CDC and ASHRAE regarding COVID-19 transmission? We all know the politics behind it. And the CDC, as announced by the New York Times on March 7th, accepted the fact that airborne transmission of SARS-CoV-2 is a real risk of transmission. And it said that people release respiratory fluids during all of the modes of exhalation, sneezing, coughing, and talking, etc., in the form of droplets, and these droplets carry and transmit infection. And it goes on to state now, inhalation of air-carrying very small droplets and aerosol particles that contain infectious virus is a real means of transmission. So we're interested to see that, and now I think we can better understand the importance of creating and designing healthier environments to reduce the risk of infection. The CDC also advocates that enclosed spaces with inadequate ventilation should be a real concern. And there are a lot of tests and studies that have been done that have demonstrated that. And of course, real life evaluations of existing exposure events and infection events, such as the Quanchao restaurant in China. ASHRAE's Epidemic Task Force on April 5th more aggressively realigned its language to say that airborne transmission of SARS-CoV-2 is significant and should be controlled. Changes to building operations, including the operation of heating, ventilating, and air conditioning systems, can reduce airborne exposures. Done. So the leading authorities have taken a firm position on airside transmission should be given every consideration in designing a building HVAC system. Well, today we're going to be looking at thermally stratified environments, and we're going to evaluate what that means and how that might differ from a mixed air environment. But first, we need to understand a little bit of the physics of room airflow. First of all, the ASHRAE Fundamentals Handbook acknowledges three means of air distribution within the space. There's a fully mixed overhead design, that was what we live with. We've been designing to for the last 50, 60 years plus. There are also mixed stratified systems where we have semi-turbulent underfloor air systems that create a semi-turbulent environment in what is called the occupied zone that we'll address later in the presentation. And then there are fully stratified environments served by displacement ventilation solutions. So let's look at the mixed air system so we can better understand why thermally stratified air systems might want to be considered for creating healthier environments. I'm going to lean on Mr. Dan Inhout and an article that he published in the ASHRAE Journal under Fundamentals at Work in 2015. And Dan goes on to express that the purpose of a mixed air system is to create an environment with appropriate thermal comfort and properly dehumidified space so we can control humidity levels within the space. In doing so, we create a uniform temperature throughout the cubic volume of space through ceiling diffusers. Dan goes on to state that the rules for a fully mixed air system involve the following. The first basic rule is that space temperatures in well-mixed spaces should be uniform within a couple degrees at all points within a defined occupied zone. Temperatures also should remain the same throughout the day, and the room must be relatively free of objectionable air currents or drafts. To do this, we supply air at 55 degrees. Why 55 degrees and not 65 degrees? The reason being, we need to dehumidify the air to control humidity in the building. And 55 degrees is an approximation of what dew point is. So we're able to wring moisture out of return air, resupply the space with air that is at a proper dew point, so we can reduce the humidity in the environment. That's why we have 55 degrees. But if you provide 55 degrees, in order to overcome convection, whereby cold air falls and warm air rises, we have to inject that air at high velocity to the space. And we do that through ceiling diffusers and high-end wall registers. And when we inject air from a diffuser at high velocity, room air is induced into the supply air stream. So in the physics of airflow, we need to understand, to get mixing in a space, there's a relationship between velocity and pressure. High pressure, as a rule, always moves to low pressure. In fact, as Dan Inhouse used to love to say, nothing sucks, everything blows. And he's right. High pressure moves to low pressure. So to maximize room air induction and mixing, we have to establish from a diffuser what is known as the Coanda effect. The Coanda effect, as defined by ASHRAE's 2021 handbook, is defined as the effect of a moving jet attaching to a parallel surface because of negative pressure developing between the jet and the surface. So high velocity means that you have low pressure air above the jet that draws the air to the ceiling surface. So low pressure air draws high pressure room air into the supply air jet. And air mixing occurs because the higher velocity equals a higher pressure differential between the supply air jet and the room air, thereby greater induction and greater mixing. So air mixing is reduced when you have a lower discharge velocity at the diffuser. You lower the pressure differential between the supply air jet, and you have less induction and less mixing. So what do we need in order to create thorough mixing within a space? We need fan energy to give us the high discharge velocity to allow for the pressure differential between the air jet and the room air condition, to allow room air to be induced into the jet for thorough mixing to occur. So when we look at airflow and supply air discharge profiles, a supply air jet will move across the ceiling when delivered at high velocity, inducing room air into that jet, creating the temperature differential over time, because as room air is induced in that 55-degree air jet coming off the diffuser, the supply air temperature increases and you begin to lose the temperature differential. Also, when you induce the room air into the supply air jet, the supply air jet becomes more massive. As it becomes more massive, it begins to lose momentum. And consequently, the Coanda effect is gradually lost from a distance from the diffuser, and the air begins to drop into the space. So when we design HVAC systems, we always make sure that these systems are designed to handle the peak summer condition or the peak cooling condition. In Arizona, we often think of it as June. And you're right, we could see 150 and we have seen up to 120, but actually the greater total load occurs in our monsoon months when we're seeing an outdoor air temperature of 98 degrees dry bulb, 78 degrees wet bulb, terms that we covered in the humidification section of this webinar series. So diffuser velocity at peak summer condition is designed at maximum, roughly 150 feet per minute. Uniform mixing occurs in the cubic volume of space due to the induction of room air, as explained. We have a uniform temperature profile, consequently, hopefully in conformance to Dan Inhouse's experience of 1 to 2 degrees throughout the cubic volume of space. And we could expect uniform distribution of contaminants consequently throughout the cubic volume of space. So to do this, a discharge velocity needs to be maintained to allow for thorough mixing. However, if we look at many of our larger buildings served by VAV systems, at part load conditions, we have a different air delivery challenge. Lower room load means that you have less supply air supplied to the space at 55 degrees. As a thermostat calls for less air because it is satisfied at its set point, let's say 75 degrees, VAV boxes modulate to a minimum position, choking off supply air. As the supply air becomes less, you have a lower volume of supply air at the diffusers and less of a discharge velocity. Cold air, otherwise subjected to the forces of negative buoyancy, exceeds the supply air jet velocity and pressure differential, and the air will just dump into the space at 55 degrees. You do not get uniform mixing at part load. The only way to overcome this, and we see this in hospitals and healthcare facilities, is to recognize this challenge. And healthcare uses reheat coils in order to overcome this challenge. What we can do is, in order to maintain the discharge velocity off of diffusers and maintain a mixed air environment, is we can elevate the supply air temperature using an electric or hydronic reheat coil and modulate the leaving air temperature to maintain space set point. However, this is not a very efficient means of conditioning a space. We use it all the time because energy has been inexpensive, but with some of the challenges we're facing today, even specifically in Arizona with our drought and lowering water levels at our main lakes, this could be a very expensive cost proposition to control space set point by using reheat. So the design challenge when we go into the part load seasons. So again, just to reiterate, diffuser peak discharge velocity occurs usually at summer months where we have the condition of maximum mixing to conform to ASHRAE's recommended guidelines. However, we're at lower volume of airflow at the non-peaks conditions in a VAV system during fall, winter, and early spring, otherwise known as cold and flu season. So uniform mixing does not occur in an environment that is seeing 50% or less of the airflow at the diffuser in a heating condition. So when a building goes into heating mode, we also have another challenge. Instead of 55-degree air supplied into the space, the reheat air temperature is 85 to 95, maybe even 80 degrees. Well, we have now under this condition positive buoyancy, so the warmer air to a space set point of 85 at low velocity discharge runs the risk of tending to stay in the upper levels of the room. So that adds another challenge. So consequently, we can rest assured that in a VAV system at a part load condition, non-uniform mixing will occur within the space. Well, there's a very important equation that was written in 1978 by William Wells and Riley to try to model the risk of infection during the 1978 measles outbreak in the Northeast. Their goal was to provide a simple and quick assessment of the infection risk. So they came up with this equation that is being used today to evaluate the risk of SARS-CoV-2. And they include these variables or these factors into the probability of infection: the number of infected individuals in the space, their average breathing rate. Are they exercising in a gym or are they in a library reading? They look at the quanta generation rate. They look at the exposure time of an infected agent within that environment and the airflow rate from the HVAC system. So here are two terms you may want to be aware of. What is quanta? Quanta is the minimum infectious viral load a droplet may contain that will result in infection. Quantum is a dose of airborne droplet nuclei required to cause infection in 63% of susceptible persons. So the quantum dosage could vary if you're trying to look at an environment, perhaps in a gymnasium where people are fit and healthy and working out, versus a medical center that might be treating people in elderly ages with diabetes and other health challenges. So the quantum level will actually vary to achieve that 63% infection rate of susceptible persons. So just be aware of those terms, quanta and quantum. You may hear them again, and quanta is utilized in the Wells-Riley equation. So there are two very compelling articles written in the May and June editions of the ASHRAE journal this year. They're called Minimizing Transmission of SARS-CoV-2 in High Occupant Density Settings. And the articles are based on a study on a well-mixed air environment as advocated by Wells and Riley. And the article introduces a modified Riley model for predicting the conditional probability of infections within indoor environments. And it says, reported here within the article is a summary of field experiments used to determine whether the assumption inherent in the Wells-Riley model that the indoor space is well mixed is appropriate. It goes on to evaluate that a modified Wells-Riley application for the prediction of infection is well suited and very effective for calculating the risk of infection for particle sizes of 0.728 microns. And they recreated this physical measurement and test chamber using sodium chloride droplets of the sizes of 0.728 microns to 2.71 microns. So they found out that for small aerosolized droplets of 0.728 microns and arguably less, you do have a mixed air, a well-mixed environment in an area that has peak airflow conditions. However, at 2.7 microns, we start to see the higher size particles of greater mass precipitating or dropping out of the air more rapidly, creating a non-uniform profile of distribution at that particle size where the Wells-Riley equation begins to break down. So this is a very important study. But the reason why I'm including this is not only to give you an interesting bit of information, but to demonstrate that even the leading tests being generated today are reviewing the conditions under fully mixed environments. I will offer this addendum to the overall presentation that we're giving today, because I think it's just too important. The article goes on in part 2 of the June 2021 volume to state that if a mask if students in a classroom and the teachers are wearing masks with an effective filtration efficiency of 0.5 or 50%, the conditional infection probability is reduced by a factor of 4 relative to the no mask baseline. And all occupants wearing masks with an effective filtration efficiency of 0.9, the conditional infection probability is reduced by a factor of 100 relative to the no mask baseline. So if any of you are still asking whether or not masks are effective or not, or should you bother, whatever, I suggest that you look at this article in the ASHRAE journal, the June ASHRAE journal of 2021. It also gave this important finding in its testing: increasing room airflow from 1.34 air changes to 3 air changes reduces the infection probability by a factor of 2. So that's an important finding, and it's the first solid report that I've seen that begins to identify air changes per hour within the built environment with an infection probability factor. So the conclusions and recommendations from the report are the reduction of an infection probability achieved with occupants wearing masks having a modest effective filtration efficiency of 0.55 versus the no mask baseline is a factor of 4x, including room airflow from 1.34 air changes to 3 air changes reduces infection probability by 2. So a combined effectiveness by using the 2 is a factor of 8 times. So pretty interesting on the Wells-Riley application, certainly with regard to the distribution of particles at 0.728 microns. So what is a thermally stratified environment? Well, let's look at thermal stratification. We've all experienced it, especially if we've been in a pool or in a lake, and we have a uniform body of water. The upper levels of that fluid are warmer than the lower levels because of the radiant energy transmitted by the sun. And we explored that a little bit in the UVC technology on what radiant energy is in that session a couple of months ago. So we very often can see, certainly in the summertime, surface temperatures in the mid-70s, but at deeper lakes, the lower water levels, that water can drop to 40 degrees very easily, depending on the depth of that body. So what is a thermally stratified building space? Well, a thermally stratified building space set to a design temperature set point of 75 degrees, supplied by air at 65 degrees, creates a thermal profile throughout the cubic volume of space of 70 degrees roughly at the floor, 75 degrees at the thermostat, 78 to 82 degrees at roughly 9 foot above the floor, depending on the amount of load, sensible load acquired within the space. What is interesting in a thermally stratified building space is the system utilizes buoyancy forces in the room generated by heat sources such as people, lighting, and computers to allow warm air to rise in a space that is set at 75 degrees. So how does displacement work? Well, it actually displaces air from the occupied zone via convection. And this is what I love about high performance sustainable HVAC. Instead of learning the rules of physics and how to apply energy to overcome the properties of physics to condition a building, sustainable high performance HVAC systems apply the rules of physics to work for us and thereby reduce energy consumption in buildings. So I have a video here to show you how displacement ventilation works. It was generated by a manufacturer. We represent Kruger, and it shows an AFB diffuser, actually 2 of them, transporting air or delivering air into a space. And on the opposite side of the room, we have a heat source. Because this heat source is 85, 90 degrees or whatever its set point might be, I don't know. You have a convective plume rising off of this heat source in relation to space set point temperature. That draws the cool air released from the diffuser toward it because of the air patterns within the space. And you'll see the smoke becoming entrained in that convective plume, delivering that smoke to the upper levels of the room via the forces of convection. And this is why displacement ventilation has been assessed as proving a healthier environment with better IAQ for building occupants. We'll explore that a little bit more carefully. Sorry about that. So just a very effective graphic that we can look at. By supplying air into a space at low velocity, at the low elevation of a room, we have a single pass of clean conditioned air across the breathing zone versus a mixed air system then, when at its best, is evenly distributing contaminant throughout the cubic volume of space at peak summer load condition. That is not the condition in a part load condition where we'll have non-uniform concentrations of contaminant and arguably pathogenic material within the breathing zone of the occupant. So if we look at how do we design thermally stratified systems, we actually inject that air at very low velocity, roughly 40 feet per minute. We can also use a VAV solution with displacement ventilation with 50% turn down. You don't want to go below 20 feet per minute discharge velocity because you just can't get the throw off of the diffuser. So this is what's important that I think is very compelling about a thermally stratified environment, is regardless of whether or not that room is at full or part load, providing the surface temperature differential of those items within the space, including a human occupant who hopefully has a body temperature of 98.6 degrees, as long as that temperature differential is maintained, a constant flow of air rises to the upper levels of the conditioned space, regardless if that system is at full load or part load conditions. So what is displacement ventilation? Well, ASHRAE wrote a displacement ventilation design guideline back in 2005, and it defines it as an air delivery solution that conditions the occupied zone, defined by ASHRAE to be 6 foot off the finished floor and 1 foot from the walls. The upper level sensible load in that space is not considered in the room load because of convection. The sensible heat load due to the conductive wall effect or due to the lighting load will stay on the upper levels of the room. Now that load will be seen at an air handler coil, but is not to be entered into the calculations for the overall room load. So when you supply displacement air, you supply it at a higher leaving air temperature of 65 degrees roughly, anywhere between 63 to 68, in lieu of 55-degree air to prevent thermal discomfort and overcooling of people within the occupied zone. And what does this mean? Well, we found out that if you supply 65-degree air in lieu of 55-degree air, you can double your economizer hours in Maricopa County. That's a big deal. Not to mention, by designing to the occupied zone, I was personally involved with Smith Group in laying out the Banner Health Maricopa Clinic, and Mo Gadarzi Smith Group actually designed it at 0.0 CFM per square foot at a time where buildings with conventional HVAC were being designed at 1 CFM per square foot. So to effectively create a thermally stratified environment, air is supplied at low velocity of roughly 40 feet per minute, certainly in a setting where there are sedentary occupants. If you have an airport or high traffic areas, you can bump that to 50 feet per minute, 55 feet per minute. You provide air at 62 to 68 degrees. The upper level room air is about 80 to 85 degrees, where your return or exhaust grills are located in the upper level of the room, drawing out that warm contaminated air from the environment back to an air handler where that air can be treated through filtration, UV lighting, or ionization. So the temperature profile within the space under these conditions is roughly 70 degrees at the floor, 75 degrees at the stat, and 80 to 85 degrees in the upper level of the room. And it has been found and proven that an occupant standing within a space will not notice a temperature differential, providing the differential is within 5 degrees from the foot to the top of the head for a standing occupant, or 3.5 degrees from a seated occupant. So that's an important factor. Any of you asking, well, aren't their feet getting cold at 70 degrees? And the answer is no, providing we do not exceed that 5-degree temperature differential. ASHRAE recognizes the better indoor air quality of displacement ventilation in thermally stratified environments by assigning a ventilation effectiveness rating of 1.2 versus a conventional mixed air system. And by the way, that 1.0 ventilation effectiveness for a mixed air system is a perfect condition that never exists. The reality in a space, due to short circuiting at return grills, non-uniform mixing and part load conditions, it really is at about 0.8 CFM, or at about 0.8, 0.85. So I was involved in physically testing the ventilation effectiveness at our installation of overhead displacement ventilation at the at the Banner Health Maricopa Health Clinic, and working with the manufacturer, Price Industries at the time, and Jerry Sipes, VP of Engineering for Price, we actually evaluated 1.3 ventilation effectiveness at the nurses station using overhead displacement ventilation. So pretty interesting findings. Now the question in displacement ventilation is, it is a very good solution for cooling, but how do we handle heating? Well, let's recap here quickly. Displacement ventilation works wonderfully in cooling mode, providing we supply air at 2 to 10 degrees below room set point, because cold air, by the force of convection, falls in pools within the lower areas of the space. We can even get mixing within the occupied zone by providing load neutral air. We don't have the pooling convection offers by supplying cold air, but we can get penetration into the occupied zone of air that is 0 to 5 degrees above space set point. However, when we go into heating mode, if we provide low velocity air off the diffuser, thermal buoyancy takes over, and that warm air will come off the diffuser and rise to the upper level of the room and not condition the occupied zone. So we have to look at ways of heating the space. Traditional ways are perimeter radiation, certainly in colder climates. I've been involved in successfully applying diffusers that are combination heating and cooling displacement diffusers. However, you do lose your ventilation effectiveness factor in overhead mixed air displacement diffusers. I think radiant cooling panels are a very effective way to go. And we can also look at fan coil terminal units conditioning with warm air perimeter walls. So here are some baseboard radiation solutions, hydronic or electric, we might consider for higher elevation locations in Arizona, such as Flagstaff, Show Low, Pine Top, etc. But here's a solution that is very effective, and that's the use of radiant panels that can become architectural features as well, where we create a temperature differential from the panel face to the surface temperatures in the room, and we actually heat the occupants themselves with radiant heat using the principles similar to those covered in the UVC seminar as we evaluated the electromagnetic spectrum. So this is a very effective way for heating in a displacement ventilation system, and I've been involved with both hydronic and electric radiant heating solutions. So what are some of the displacement ventilation products that are available? Multitude of different diffusers. Because we need to provide the minimum air to satisfy not only the space conditions, but also the ventilation requirements of the space, and we're supplying air at low velocity at 40 feet per minute versus 150 feet per minute, you need a wider surface area of diffusion to do so. So a displacement device will be traditionally much larger than a conventional 2x2 diffuser in the ceiling. But there are many different solutions that are out there, and they are very easy to adapt to custom configurations that architects might find rather appealing. There are rectangular, recessed in-wall diffusers. There are corner semicircular diffusers. There are ceiling lay-in diffusers that I've had great success with. However, per ASHRAE 62.1, I'm sorry, it's 2019, sorry for the typo. If you use overhead displacement that I've applied successfully in a number of projects, especially Banner Health projects, you will not get the 1.2 ventilation effectiveness with the overhead design. There are semicircular diffusers with large airflow capacity that we can dump a lot of air into a space and just let the air crawl to the heat sources. There are underfloor air solutions. There's underfloor displacement ventilation that we have installed at ASU's McCord Hall. That is a displacement diffuser device that provides air at low velocity and allows literally for a more effective single pass of clean air across the breathing zone than a low in-wall solution that only has a distribution capability of 30 feet from the diffuser face. And then there are the underfloor mixed partially stratified solutions where we inject air at a higher velocity off of a floor diffuser, creating a micro mixing zone within the occupied zone and allowing for thermal stratification to occur above that occupied zone level. ASHRAE, not too long ago, has accepted the fact that a mixed partially stratified underfloor solution does qualify for the 1.2 ventilation effectiveness rating that the standard calls for, giving you an opportunity to design these systems with 20% less outside air. So if we have to supply 65-degree air, then the question should arise, well, how do we dehumidify that air at 65s? We're not hitting dew point. There are air handler considerations to be aware of. And by the way, ASHRAE Standard 62.1 has moved away from relative humidity as a gauge for what we should design a space humidity level to be. It is not relative humidity anymore that is dependent upon temperature. They use dew point, which is more effective in evaluating the moisture content in the air because dew point is a value that is not temperature related. So the question is how do you dehumidify 65-degree supply air? Well, one solution that I've had in my designs is a technology called side stream bypass. Side stream bypass allows for mixed air to be injected into the supply air stream that has been conditioned at the cooling coil. And by putting a discharge air temperature sensor on the discharge of the air handler, we can modulate the bypass damper to maintain a constant leaving air temperature of 63 degrees, and then just let it and just ride that damper. But we do have to be careful of what design dew point we provide off the cooling coil. I was just involved in evaluating an air handler for an underfloor system that we're looking at for a project. And the air handler manufacturer provided us 55, 54 degree off the cooling coil in a side stream bypass configuration. Well, that meant the dew point coming out of the air handler, the supply air coming out of the air handler was 55 plus degrees. Well, conventional HVAC designs supplying 55-degree dry bulb, 54-degree wet bulb supply air has a dew point of 53 degrees. So at 55 plus dew point on the configuration the air handler manufacturer gave us, we were compromising latent cooling. Consequently, we had them redesign the cooling coil, expand it a little bit so they could give us 49-degree dry bulb temperature off of that coil. So when mixed with mixed air, we could get the 53-degree dew point out of the air handler. So these are design factors engineers would want to be aware of in laying out these air handlers. We can also provide desiccant dehumidification solutions. We can do dual wheel designs to control that leaving air condition out of these units. The side stream bypass solution I used working with DHE engineers at the Banner Boswell Medical Center worked extremely well, and it controlled the leaving air temperature at 65 degrees using a side plenum bypass solution where we took mixed air that was filtered and then dumped it post coil to maintain the leaving air temperature out of the air handler, and then we put the final filters downstream. Another solution is a dual wheel configuration. In using a dual wheel configuration, we can use an enthalpy wheel to use return air or exhaust air from a building to precondition the outside air. We have dehumidification at the cooling coil, and then we have a sensible heat transfer wheel after the coil where we can post-heat the air off of the coil to the design leaving air temperature that is necessary for the space. And for larger projects, this gives you tighter control of your leaving air temperature. And this is what we used at the ASU Student Pavilion in that active chill beam design solution, and it worked very well. So if we take the idea of a thermally stratified environment, how can we apply it in 100% outside air solutions? I think with the challenges of pandemic, the costs that flu and cold season offer employers in sick time is significant. And I think the era of pandemic has demonstrated that proper precautions, though unfortunately excessive due to the nature and aggressive nature of SARS-CoV-2, we did not have a flu and cold season this year. Consequently, we might want to ask, what is the cost of that sick time due to flu and cold during our worst time of year for creating healthier environments? Well, 100% outside air systems offer a compelling solution. I want to say that if anybody has any questions on how to evaluate what these systems might be, depending on the building type you're designing to, we'd be more than happy to assist in evaluating what might be a good solution for your space. But what I like about 100% outside air systems using a passive component is the fact that we have no return air from the building back into the supply airstream that we would see even in a conventional displacement system in creating thermal stratification. How does such a system work? We actually provide 100% outside air into the space close to the minimum ventilation value of that space. In our environment with our high summer conditions, we may need more than the ventilation air. And then we put a passive component in the space, and we want to have a thermally stratified environment, so we increase the delta T, or the temperature differential, to the cool air at the passive chill beam shown in this diagram, so that we have a conductive flow effect off of that air into the space for sensible cooling in that space. This way, we have a thermally stratified environment with clean outside air passing through the breathing zone with no return air brought into the space. Return air that is going to pick up pathogens accumulating throughout the occupied hours, and then if not properly treated through filtration, UV lighting, and/or ionization, then that pathogen is re-injected into the space, because we've demonstrated in the pathogen mitigation session that the lifespan of desiccated virus can be up to 72 hours. So something to keep in mind. I think 100% outside air systems are very compelling. Plus, we are seeing 40 to 50% energy savings as being modeled by some of our leading design teams, such as Smith Group and HDR. So something to be considered. And I'm confident AEI is finding these same results. Also be aware that we can participate in evaluating displacement ventilation using variable refrigerant systems. Variable refrigerant technology makes all the sense in the world. And yes, we do have an installation of a VRV coil kit in a Daikin air handler in an existing underfloor system at the Butler Design Studio, working extremely well. So that's a whole other conversation I'd be happy to have with you. Please understand that if you do displacement and you're looking at maximizing the indoor air quality of your space and reducing the risk of infection, we invite designing that space as well to 40% RH. Use UV lighting if you have return air back to your displacement air handler, and look at applying ionization. And that concludes today's presentation. Are there any questions?
There are not currently any questions in the chat. So if anybody does have any questions, you can type them in there, or feel free to unmute yourself and ask. It's always that moment of awkward silence. All right, well, if you decide later that you do have questions, feel free to email me. I can pass it on to Dan. You can also email Dan direct, or contact your local salesperson for help as well. So if there are no questions, we can wrap this up. Dan, any final words?
No, thank you very much for your time and today. We hope you found the information relevant and of interest. And of course, if you think of any questions, don't hesitate to reach out to Kelly or myself. We'll be happy to answer them.
Awesome. Thank you so much, Dan. Great job.
Thank you.